In this section, we're going to actually look at the reactions of ethers and kind of the opposite of the Williamson ether synthesis. We're going to look at destroying ethers. So here we have the product that we made before, the ethoxybenzene, like we made before. But instead of making it, we're actually going to destroy it. So we have HCl, H2O, and we reflux. When we do this, what we end up with is the alcohol and the alkyl halide, in this case, the chloride. So this is kind of the opposite of the Williamson ether synthesis. Remember that in the Williamson ether synthesis, this was an alkoxide, but in HCl, that can't exist. So that would easily be protonated to form the alcohol. So it's kind of the opposite of the Williamson ether synthesis. Now in this example, you may wonder, why is the OH here and why is the Cl here? So let's look at a different example that illustrates this a little bit better. So what we have is, we have a CH3, CH, bond O, CH3, CH2, CH3. So we have an ethyl isopropyl ether. So they're asymmetric and they're different. We add HI. Well, what's going to be the first step of this reaction? Well, the first step of this reaction is the protonation of this molecule. And what we end up with is CH3, CH, CH3, bond O, CH2, CH3, bond H. And then the question becomes, well, which direction is this going to go? How is it going to break? Is this going to break off and form the alcohol, or is this going to break off and form the alcohol? Well, remember that this is going to undergo an SN2 type of mechanism. I guess not remember, but this is going to undergo an SN2 type mechanism, which means we need one of these two things, this or this, to be the leaving group, and we need I- to come in and kick it off. Well, in this case, I- is going to be more likely to come in here. And the reason for that is steric hindrance. This carbon is more sterically hindered than this carbon. This carbon is secondary and this carbon is primary. So the less sterically hindered carbon will be attacked. And when we draw our transition state here, what we end up with is our CH3, CH, CH3, OH coming out. We have a C with two H's. That's this CH2. We have the I- coming in, and the CH3 here going along for the ride. And this is a transition state. When this is all over, what we end up with is CH3, CH, OH, CH3 plus CH2, now attached to an I, and still attached to that CH3 here. So what we end up with is that the halogen gets attached to the less hindered carbon because the attack there is easier in this SN2 type mechanism. So this is a relatively short section, so I'm going to combine it with the next section, which is the Claisen rearrangement. And a Claisen rearrangement is actually an interesting process because we see, as you could probably guess by the name rearrangement, that a carbon-containing group jumps. So this is called the Claisen rearrangement. In the Claisen rearrangement, if we start with, and this involves an allyl phenyl ether. All right, let me move that down so you can see it. An allyl phenyl ether. So let me draw an allyl phenyl ether. We have an O, CH2, CH, double bond, CH2. Okay, so it's phenyl because that's a phenyl ring. It's allyl because this double bond is one carbon away from this. So 1, 2, and the second carbon we have the double bond, so there's one carbon in between. That makes this an allyl phenyl ether. If we do this and we heat it up, all right, to 250 degrees C, we can get something interesting to happen. And what happens is we get the alcohol on this side, and this actually jumps. So what we end up with is a CH2, CH, double bond, that should be just one H, CH, double bond, CH2, okay, like this. So this part actually jumps over here. The H that was here actually ends up here, so we have a rearrangement. Now why this happens is because we have a 1, 2, 3, 4, 5, 6 membered ring that is possible. So what I'd like to look at is the mechanism of this, but I want to draw this a little bit differently in order to make it a little bit more clear. So the first thing I want to do a little bit differently in the mechanism is I want to draw my bonds in my benzene ring like so. Now I have an O bonded to a CH2, that's that one, bonded to a CH, that's that one, double bonded to a CH2, that's that one. So I have the same thing. I have a 3-carbon group attached to the O, a 3-carbon group attached to the O. The only difference is I drew it so it can seemingly make a ring. So what's going to happen is these electrons are going to go here and form a new bond. These electrons shift here, and these electrons shift up onto oxygen in this rearrangement. And what we end up with is this. These two double bonds go along for the ride. This oxygen now has an extra lone pair and a minus charge. We now have this carbon bond with a CH2. This is now a CH, and this is double bonded to a CH2, like so. All right, so this is basically how this happens. We have an H here. Now this molecule can resonate, where this lone pair goes down here, and what we end up with is this molecule double bonded to O. We have an H here. We have a CH2, CH, double bond, CH2, like so. Now, if you remember back to the aromatic chemistry, this is probably not likely to be stable. And the reason for that is we've lost aromaticity. So we went from something that was aromatic to something that's not aromatic. So now we need a way to regain aromaticity. Well, if we have some base minus here, okay, anything that's capable of taking a proton, then what's going to happen is it's going to grab that. When it grabs that proton, this jumps back into here, and that jumps up onto there. And we've re-established aromaticity, which is very important for stability. So we get CH2, CH, double bond, that should be a C, CH2, and now we have an O minus, because we dropped those electrons back onto O minus. We now have H base, right? Whatever took off the proton now has that proton, and this can grab it. And at the end of the day, we get our product, which we have the alcohol here, and we have CH2, CH, double bond, CH2, like so. So this is the mechanism of this reaction. Now, if we have a allyl vinyl ether, all right, instead of a phenyl ether, if we have an allyl, I gotta make sure I'm on the screen, vinyl ether, okay, it's going to be a little bit different. In this case, let's take this example. We have CH2 double bond, CH, bond O, CH2, CH, double bond, CH2. So it's vinyl on this side, allyl on this side because we have the CH2 in between the double bond, and vinyl on this side because there's no CH2 in between. We just have the oxygen directly bonded to the C double bond O, to the C double bond C, excuse me. So this is basically what we have. Well, this can also undergo a rearrangement. And in order to understand the rearrangement that it undergoes, I think it's important to label the carbons. So I'm going to label this one 1, okay, this one 2, this one 3, this one 4, and this one 5. Remember that it's going to break about this oxygen. So this one is 1 because it's going to be staying bound to the oxygen. Now, if we look at carbon 1, it's going to form an aldehyde, okay? And the reason for this is we don't have to regain aromaticity. If you look at the previous example, we formed a ketone, and the only reason the ketone didn't stay is because in the mechanism we needed to regain aromaticity. And when we did that, we couldn't have a ketone anymore, right? You can't have a ketone attached to an aromatic ring, and this became O-, which then needed to be protonated. But in this case, we don't have that problem. We're not going to regain aromaticity anyway. So carbon 1 becomes double bonded to an O. And essentially what's happening here is we're forming a 6-membered ring, and these electrons are coming in here, shifting this over here, and breaking this bond. So carbon 1 is going to have a C double bond O. Then carbon 2 is going to lose this pi bond, which is now going to form this new bond with carbon 3. So it's no longer double bond between carbon 1 and carbon 2. Now carbon 2 is bonded to carbon 3, like so. This double bond shifts over, so there's no double bond between carbon 3 and carbon 4, but there is a double bond between carbon 4 and carbon 5. So we end up with a similar type of arrangement with this allyl vinyl ether. The major difference here is that we end up with the aldehyde. We don't end up with the alcohol on one side. So this is how the Claisen rearrangement is going. So let's look at 2 examples of how you could be asked about this. So let's take an example here where we have an O, all right, and we have a double bond like that. And we add some heat. What are we going to form? To me, it's really important to number these things. So in this case, I'm going to number this one as 1, this one as 2, and this one as 3. Since I have the benzene ring, I'm going to form the alcohol on one side. Carbon 1 will become attached to the ring. Carbon 2 will kind of go along for the ride, and this double bond will shift between carbon 2 and carbon 3. So what I'll end up with is a ring attached to an OH. That's this part. Now this will be carbon 1. All right, remember that initially this double bond here makes this new bond, and then this bond shifts, and then we reform aromaticity. Carbon 2 will be like this, but now it'll be double bonded to carbon 3, like so. Let's look at another example. And I realize these are the same examples that we already did. I'm just showing them a different way. So here we have an oxygen, and here we have a molecule like this. So we have an allyl vinyl ether here. So in this case, I'm going to call this 1, this 2, this 3, this 4, and this 5. In the case of an allyl vinyl ether, what we're looking at is on the side where carbon 1 has a double bond attached to it, and it's directly attached to the O, that is the side that's going to retain its bond to oxygen. So when we add heat to this thing, what's going to happen is carbon 1, which I'll draw that way, is going to now be double bonded to O and bonded to an H. Carbon 2, which used to be double bonded to carbon 1, this double bond is now going to be the bond with carbon 3. Carbon 3 and 4 used to be double bonded, but that double bond is going to shift between carbon 4 and carbon 5, like so. and then this bond is going to break, and that's how we get the double bond here with this aldehyde. So these rearrangements are a pain in the neck, and they take practice. I strongly recommend that you write these things out a couple times so that you have practice and you can see where the different carbons are going in these examples.